All right, so here we go. So 13. We've got this fancy cockroach with a mass of m. He's on the rim of a uniform disk with a mass of 4m. So let's draw this. So here's the disk. This thing has a mass of 4m. At the outside edge is our creepy cockroach with a mass of m. And it says the disk can rotate freely about its center like a merry-go-round. Initially, the cockroach and the disk rotate together with an angular velocity of 0.26 radians per second, right? Yes. Then the cockroach walks halfway to the center of the disk. What then is the angular velocity of the cockroach disk system, and blah, 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 blah. Okay, great. So this is my initial setup, and then what's going to happen is the cockroach is going to walk halfway to the center of the disk, so to here, and the question is, what's the angular velocity then? Good?
Yeah.
All right. So first of all, do you guys understand why, based on what I just kind of walked you through, does it make sense to approach this from a momentum perspective?
Yeah.
I mean, it's the figure skater pulling their arms in, right?
Yeah.
Okay? So what we want to do then is we want to say, all right, well, our total angular momentum before the bug moves has to equal the total angular momentum after the bug moves. All right? So that means the angular momentum of the disk initially plus the angular momentum of the bug initially has got to equal the angular momentum of the disk final plus the angular momentum of the bug final. Cool?
Yeah.
So this is rotational inertia of the disk. So the rotational inertia of the disk is 1/2 mr squared, right?
Yeah.
But my m is actually 4m, right?
Yeah.
So I've got 1/2. The mass is 4m. It doesn't actually give us a radius, does it? So let's give it a name. Do you want to just use r?
Yeah.
R over 2 for the disk.
Yeah, I think the r's are going to not matter. All right, so r squared. So that's our I, right?
Yep.
Times omega, which is 0.26. Follow?
Yep.
Plus, now we're going to do the same thing for the bug. So rotational, well, no, we can't do mrv because we don't know the v.
MR squared.
So we got to do mr squared. So that's literally m because the mass of the bug is m. Radius is r squared. So there's our I times again our omega. Okay, so that's all of our initial information, which I had meant to do in red and I didn't. I apologize. Everybody good? Equals, what's going to change on the other side of the equation?
The radius of the omega.
Which, so,
No, your radius. Omega will change.
so let's do the disk. So for the disk, I'm going to have 1/2, what?
4m.
4m. Do I divide my radius by 2?
No.
No, because the radius of the disk has not changed, right? It's still the same disk, but now it's got a new angular velocity, right? Follow? Plus, what?
R over 2 squared.
r over 2 squared, right? Because our bug has moved to the center of the circle. Times omega f. The same reason that, yep. Yeah, so we've changed the rotational inertia of our system now. So I guess the important thing to understand here, you guys, is the bug and the disk always have the same angular velocity, right? Because the bug is basically just sitting there on the disk, except for during the time it's moving. But bless you. All right, everybody good? All right, so we're happy because what happens?
MR squared.
All the mr squareds cancel out.
With a 1/4.
So let's see. So on this side of the equation, you get
0.78.
0.78. Thank you. Equals on the other side, you're going to have 2.25 omega f, and then divide, and you get your omega f. Follow?
Yes.
Okay. Everybody else good? I hear Peter saying he's good. Is everybody else good? Okay, cool. All right, so I guess we should. Is there any value in doing that? So that's going to give you some number, right? Okay, so let's see. So so that's part B or part A, and then B wants to know the ratio of the kinetic energy. So basically, at this point, you go through. And do I need to do this part? Find the kinetic energy before he moves, find the kinetic energy after he moves, and just find the ratio?
And that's rotational kinetic energy.
Rotational kinetic energy, yeah. And I think, even though you don't know the mass, I think everything cancels.
And that's the rotational kinetic energy of the disk plus the bug.
Correct.
So it would change the total.
The kinetic energy, yeah. Yeah, so when the figure skater pulls her arms in, her inertia decreases and her angular velocity increases proportionally, right? Because of conservation of energy. Or because of conservation of momentum, sorry.
Yeah, this 1/2. Okay.
But the squared means that the velocity is more important than the inertia.
Okay,
So yeah, so we're going to actually gain energy here.
that makes sense.
Okay? Follow? All right, is that enough for 13?
Yeah.
Okay, cool. Let me stop there then, so that we have some time to talk about some other stuff. So let's do one of those, one of the pendulum-y ones.